So we have this ball rolling down. It's a simple energy problem. As long as you remember that when a ball is rolling, it has kinetic energy from the actual translation, the 1/2 mv squared kinetic energy, as well as the rotational kinetic energy, 1/2 I omega squared. So we start from conservation of energy. It rolls without slipping to the bottom. So conservation of energy tells us that all the kinetic energies and all the potential energies initially add up to this total mechanical energy before, which equals the same as the total mechanical energy after. The ball is released from rest, so it initially is going to have no kinetic energy. We're going to call this level the zero potential energy mark in terms of gravity, okay? Gravitational potential energy is 0 here. And so over here, actually I'll draw it on this side, U equals 0. So over here, U is going to be equal to mgh, where h is the height. Does that make sense? For the potential energy? So it starts with that much potential energy. So we're going to have the mgh initially. There's no spring in this problem, so there's no other type of potential energy. It's all gravitational. In the end, it's going to come all the way down to what we call the 0 mark. So it's going to have no potential energy in the end. And the final kinetic energy, the key to this problem, is that it's the final translational kinetic energy plus the rotational. So a ball, some sort of box that was just sliding down with no friction at the very bottom would just have this. But if the thing rotates, it has the rotational component as well. Now, as a side, anything that's rotating, that means that the actual speed of the edge of the thing that's rotating is r omega. So, and the speed of the edge of the part that makes contact with the ground moves at the same speed as the whole thing. So in general, for these types of problems, it's important to remember that r omega is the speed that the thing moves at. So the speed is r omega, or omega is v over r, is going to allow us in this equation to replace this omega with v over r. So now our equation just has the v in it, which is the thing we're trying to find. And the rest we know. So we just start plugging things in. The mass is 4.6, 9.81 times height. If you can calculate that for me, that would be awesome. And then we have 1/2. Same thing for the mass of 4.6 v squared, and then 1/2. The I, I'm going to solve for the I in a second. And then the v squared over r is v squared over r squared. The radius is, do we know the radius? No. Okay, the radius might cancel out. Let's see. Calculate the speed at the bottom of the incline. Okay, we're probably going to have to write I in terms of the radius, and it'll cancel, okay? So we'll leave the r squared. We'll leave it as an unknown. Let's solve for the I. The I is a solid homogeneous sphere. You could always Google it, and you would find that a solid sphere is 2/5 mr squared. If this was on a test, you'd be given that equation. You can also look in your textbook, but you don't have to memorize these. So 2/5 mr squared because it's a solid sphere. If it was hollow, you'd use the thin one, thin spherical shell. So 2/5 mr squared is what our I is. So let's just solve for it down here. I is 2/5 mr squared, which is 2/5. The mass of this thing is 4.6 r squared. Can you tell me what the 4.6 times 2 over 5 is, please?
Yeah.
1.84. Is that what you got as well? Okay, so we're good. 1.84 r squared. That's the moment of inertia in terms of the radius of the ball. But as we saw a second ago, we didn't actually need the radius. Regardless of how big the sphere is, it's still going to, this r is going to cancel. This r squared is going to cancel. So that's an interesting side note of this problem. The speed at the bottom of the incline won't care how big the radius was. Now, the rest is solving for v. Did someone solve for the left side before by any chance?
52.80.
Thank you. 52.80 equals, this is 2.3 v squared plus 0.92 v squared. And then we just combine these and divide through. You can just give me the final answer if you've got it. And take a square root at the end. 4.05. You get that as well? Let's see if we get the right answer. You got 4.05? So we're probably right. Calculate the speed, put our units, and that's it. That makes sense?
Yeah.
Yeah.
And for the determine the kinetic
Oh yeah,
energy,
there's an extra part to this. Thanks.
you just plug it in.
Determine the rotational kinetic energy of the sphere at the bottom. Yeah. So let's just do that over here. The rotational kinetic energy is this thing not working? Okay, that's not working. We'll go back to notebook to do it. The rotational is the 1/2 I omega squared. That's this thing that we had, which actually we know is 0.92 v squared. Okay, I'm just going to spare us the math because we already did it over here.
Yeah.
That's 0.92 v squared, which is whatever, 0.92 times that squared, if someone wants to do it for me.
Yeah.
15.1. Okay, and that's an energy, right? So we put our units. That's joules. So 15.1 joules is how much rotational kinetic energy it has at the end. That makes sense?
Yeah.
Okay, so the key is just not to forget when something's rotating, it has two types of kinetic energy.